So good afternoon. Hi, I am Jia-Yuan Dai from National Zhongxin University. So yes, I am a mathematician. So today I won't show you many experiments, but I will bring some new ideas, and I hope that these ideas can help to bridge our disciplines. And today in my talk, there are indeed two keywords: spiral wave and pattern selective feedback stabilization. But I will highlight more about this methodology, pattern selective feedback stabilization. And the spiral wave is just an application. So before the methodology, I want to explain why I study spiral wave. Because spiral wave appears in many phenomena like physiology. Because because spiral wave can appear on the propagation of electrical wave on hard tissue. And if your heart has some problem, then you see spiral formation here. And also, you can see spiral from the very famous glucose chemical reaction, and also in the Ginsburg-Landau theorem of superconductivity, you also see spiral wave. And so my research focus is to explain, predict, and also control the dynamic of spiral wave in mathematics. And today, before to reach my results, I want to explain some main concepts. Okay. The first one is pattern. What is a pattern? Pattern is what you can see from experiments or simulations. So I say this is a representation of some spatial temporal structure. So you see a spiral, it is rotating. So this is spatial temporal structure. And a pattern is called predictable. It's very easy. It's just a solution of a prescribed model. So if I have a Ginsburg-Landau equation, it's a partial differential equation, it's very difficult, annoying, but it's just an equation. But with this model, if it's a solution like spiral wave, then I call it a predictable pattern. And in mathematics, the predictivity is about the existence of solutions. So now I have a pattern. And the second question is, a pattern can be observable if it's robust under environmental errors. What are environmental errors? There can be a wrong error from simulation or from when you do experiments, there must be some error. And in mathematics, observability is about the stability of solutions. So if a pattern is stable, then it is robust under errors. So you can see stable patterns. So here I say stable patterns are predictable and observable. So in some sense, I said it's scientific. Scientific. Scientists like stable patterns because they can see from experiments. But indeed, mathematically, there are so many unstable patterns. They are solutions, so they are predictable from the model, but unfortunately, they are not observable. So what should we do? Is it just a byproduct of pure mathematics? Okay, so the goal of my research is, now I have some unstable patterns. I want to make them stable. So this is stabilized. I want to stabilize unstable patterns. And how? By the so-called non-invasive feedback control. Okay? And here there are several keywords. The first one is, what is a control? A control is an implementable modification of a model. So you have a model. Now you want to modify. You add some term, you multiply some term, you change the model. If this modification can be implemented in numerics or in experiments, that is a control. Now, for a target pattern, so suppose I have a spiral, then a control is so-called non-invasive if the pattern is still a solution of a control model. This is very important. Why? Because I change my model. I have a pattern. It is not necessarily a pattern of the control system. But if my control is non-invasive, the pattern is still a pattern of the control model. So here I have a remark. Invasive control makes the target pattern disappear. So this is very bad because you want to observe something, but now this pattern disappear. Okay, by your control. So non-invasiveness is very important in applications. And then what does stabilization mean? Stabilization is a design of a non-invasive control that makes a target's unstable pattern stable. So one sentence, take on place before my talk is, my goal is to see the invisible. Okay. this is the first equation you see, but you see, I don't specify linearity f. Okay, so it's quite general. You have a model like so. This is an ordinary differential equation. You have a model. Suppose this model from this model you can prove there is an unstable periodic solution, periodic oscillation, say in chemical reactions, and the period is p. So this is unstable. It's predictable from the model, but you cannot observe it. You cannot see it. Now, the Pilatus control in 1992, he has a very clever idea. He introduced this term. This term is a control term. It's non-invasive. Why? Because here you see the time delay. The time delay is a multiple of a period. So if you substitute this set with this p periodic pattern, then this control term disappears. So this means that the periodic pattern is still a pattern of the new of the control system. And the main goal is we can choose some time delay and also feedback gain such that the control model, the pattern becomes stable. Okay. So the main point here is you can use the time delay, the feedback control of time delay to make something feasible. So there are advantages and applications. So Pilatus control is very popular, so there are so many citations. Because why? Because you just need very detailed knowledge on the target pattern. In the previous slides, you just need to tell me what period you want to have. And it's model independent because remember, I don't really specify the equation, what the equation looks like. And it's also its implementation is cheap. So I am not a scientist, but according to the literature, this time delay can be implemented by laser, by optics, and I will show the experiment later. And because it's model independent, there are so many applications. For example, you can chaos control in chemical reactions, synchronization, also optical control. So now I think this is the most important slide, but I am very weak in it. Okay, so I want to show example of photosensitive neutral substituency oscillator. This is a BZ oscillator. And this experiments were conducted by my collaborator Isabel Schneider in Berlin, Jan Post in MIT, and also these two collaborators in TU Berlin. So what do? They have this BZ chemical reaction in this piece. Okay, here you see a chemical reaction chamber. Okay, then there is a plate. On this plate, there are so many bits. Each bit is an individual BZ reactor. Now there is a projector. Okay, it projects light into this chemical reactor, and then this light will give coupling for the hexagonal network and also feedback. Okay, so and then there's a filter, and the camera will record the light and then send to the computer. The computer will calculate and give a new feedback back. Okay. And here you see this is a schematic picture. There are so many bits, and this coupling are in this symmetry of the hexagon. Now, what do they see? I think this is the most important slides in my talk. The left panel, the left row is color is for simulations, and the right panel, right color are for experiments. And here you see the horizontal line is 5, the vertical line is 6 nodes because we have a hexagon. If there's no control, then you see the fully synchronized pattern without control. Okay, and the gray values are these fluorescence signal. Yes, but now you can apply certain Pilatus control such that you see what you see the anti-phase. You see the anti-phase pattern. This kind of these three, okay, and then you can see two other patterns with more intrinsic symmetry. I want to emphasize these three patterns are predictable. They can be proved as a solution from the model, but you can never see it from experience because they are unstable. You can prove it by mathematics. But now with this control, you can select one pattern. Okay, you want to see this one, then you apply the control I propose, and you see this one. Okay, and this kind of stabilization is selective in because you can just see this pattern and all other patterns, they just disappear. So this is main result. Sorry, this is a second also different equation, but okay. But I just want to tell you that this kind of control was ODE. There's only time delay. But this year we generalized to the so-called Gibbs-Blandar equation. Okay, Gibbs-Blandar equation is a PDE. So we have a time delay, or we have a time and also space. So here I just want to highlight that in this PDE setting, our control can be more flexible in the sense that we can consider control triple. So for example, we can have this H, this is multiplicative factor, and we can have a time delay, okay, and also space delay. And space delay is indeed the notation of the domain. If I consider this as my HT, so we can have a special temporal delay. And now this is a mathematical theorem. We can prove, this is a mathematical proof, that are abundant control triples, okay, that stabilize spirals in a pattern selective way. What does that mean? There are so many spirals you cannot see from numeric and from simulations. But now, if we apply our control, you can see exactly what you want to see. Okay. So it's a summary for so it's a summary of stabilization. Why do we need stabilization? Because it makes unstable patterns observable. So now for scientists, you have more patterns to play with. You can decide, okay, based on this new observable patterns. And how? And today my methodology is feedback control of spatial temporal delays. And why is it ongoing? The cutting edge research have two aspects. The first one is people are doing experiments on pattern selective stabilization with many spatial temporal symmetry. This is an ongoing cutting edge research. And also mathematically, there is a fast development of math for spatially extended models or PDEs. And here I want to, I would like to invite or indeed request, okay? There's an open question like for scientists. Experiments on pattern selective stabilization in a spatially extended models are still open. And there are many important examples from such models, like traveling wave, okay, rotating wave, and spiral wave, and score patterns, and even more. And so this is my talk. Thank you very much.